Hi, my name is James Horng. So the problem I'll be solving today was given on the second exam in the fall semester for Chem 101. It involves ranking 5 species from the lowest to the highest ionization energy. So ionization energy is defined as the amount of energy required to remove an electron from the atom. So looking at this problem, there's something worth noting is that 2 of these species are ions. So we have to think about the relationship between an ion and the ionization energy for that ion. So the first thing we can look at is chloride. So chloride is an anion, which means that it has more electrons than it does protons. This means that the overall pull on the electrons it's less than I guess usual than its neutral counterpart. This means that the ionization energy, or the energy required to remove an electron, is much lower than usual. This is because there is less of a pull on those electrons because there are less protons than there are electrons. On the other hand, aluminum is a cation, which means that there are more protons than there are electrons. This means that there is a greater pull on the electrons because there are so many protons. This means that the energy required to remove an electron is much higher than usual. You can think about it in you can think about it this way. So, say you have $2, and someone approaches you asking for $1. You are more likely, and you give them that dollar. You might be kind of hesitant to do it, but you can afford it, so you give them the dollar. Now, if someone comes up to you again and asks for another dollar, then you're less likely to part with your remaining $1 because once you give up that $1, you have nothing left. So, in the same way, it works for these ions. So the anions have more electrons, or kind of like more money, so they're more willing to give up those electrons. And cations have less electrons or less money, so they're less likely to give up their electrons. So, chloride will have the lowest ionization energy, and aluminum will have the highest ionization energy. So the remaining 3 species are all neutral. So we can determine the ionization energy by looking at 2 things. We can look at N, which is their valence shell, and then the Z effective, which is the amount of protons minus the amount of non-valence electrons. So N is very easy to determine. We can look at a periodic table, and we can look at which row it's in. So chloride will be in the 3rd row, potassium is the 4th, and sodium the 3rd. So those are the N values for these 3 species. Now, Z effective is a bit trickier, so we have to first determine the amount of protons. So we can look at the periodic table and look at the atomic number for these. So for chlorine, it will be 17. Now we have to determine the amount of non-valence electrons. So one way to do this is to write down the electron configuration for the species. So for chlorine, it would be 1s2, 2s2, 2p6, 3s2, and 3p5. Now we determined earlier that the 3rd shell is the valence shell, so these electrons are going to be the valence electrons. So that means these 10 electrons in the 2nd shells are going to be the non-valence electrons, which add up to 10. So the Z effective would be 17 minus 10, which is positive 7. We can do the same thing for potassium and sodium and get 1 plus for both of the Z effectives. So we have to think about the relationship between Z effective and ionization energy. So the greater the Z effective means the greater the pull on the electrons. So the greater the pull on the electrons, the less likely it is for those electrons to be lost. So the greater the energy required to get rid of those electrons. So Z effective and the ionization energy of that atom are directly related. Now, on the other hand, N, which is basically the size of that atom, is inversely related to ionization energy. One way to think about this is that it is much easier to keep something safe. It is much easier to keep something safe when the item is closer to you than when it is farther away from you. So the closer the electrons are to the core of the atom, the stronger the pull on those electrons will be. So looking at these 3 species, we can see that chlorine not only has or one of the smaller N values, but also has the largest Z effective. This means that this atom is going to have a pretty large ionization energy. Potassium and sodium, on the other hand, have the same Z effectives, but they have different Ns. So the smaller the N, the greater the ionization energy. So sodium has a smaller N than K, or potassium. So sodium is going to have the smallest ionization energy next to potassium and then next to chlorine. So that's the order for the neutral species. Wait, just kidding. It's the other way around. My bad. K is less than C. And yeah, this makes sense because N is bigger for K, or for potassium, so that's a less ionization energy. My bad. So this is the order for the neutral species, and we determined earlier that the anions have the lowest ionization energy because it has so many electrons to give away, and that the cations have the highest ionization energy because it has so little electrons to give away. So the order of the 5 species from the lowest to the highest ionization energies would be chloride into potassium into sodium into chlorine into aluminum. And that's how you would solve this problem.